Yeah, then welcome to our last meeting in the summer term 2025 about parallel and distributed computing. So we'll not exercise today and not lecture today, but instead we look at the exam, which is an exam that I believe I had last year or so. And yeah, so this is similar to the exam that we will have. There's always a problem that I say up front. Maybe your colleague is still coming in this time. It's always the question whether we hand out the exams that we have given, or we keep some back and then repeat these. So this has advantages and disadvantages, in particular for you. I mean, also for me, because I always have to think about new things. But one thing that we observe is if we give out exam, we always have to invent new questions, and because we've done all the obvious easy questions already, this kind of leads to getting exams not necessarily easier over time. Yeah, so you should be happy with your professors who do not give out the exams. Yeah. Yeah. So having said this, yes. So how does this work? We have. Okay, I always keep the structure the same, yeah, but the content will be different. So we'll have some parts that is questions that are different from the others. So questions here in this case, I hope 30 points. Sometimes I made a mistake here. Then we'll have several questions, out of which, so there will be 5 questions, out of which usually I believe 4 will be directly programming questions, and 1 may be a little bit more abstract. Yes, so I have a tendency, I cannot promise that this is always the case, but I kind of have a tendency to put the question that takes the longest time to do to the end. Yeah? And I also have the tendency to make exams not necessarily of the kind saying that this is the amount of things that you have to do, yeah. But I'll in the last. So my last question is usually this kind, so that everybody has something to do during the exam, so that it may take a longer time. But so that should not encourage you not to do it, because and with these questions these kind of questions are usually the ones where you get where it's easy to get partial points, yeah, by not finishing. So, start it and try to get to something, yeah. Okay, so we have the style of putting as many points as we have minutes, yeah. So the number of points indicate the amount of time in minutes that should be used to answer the question. Justify your answers with clear explanations or calculations that show how you arrived at them. Yeah, so if you just write a number, it's always 42, right? So you know this already. You need to write in a readable style. Unreadable answers do not count. And there is a fun thing that is usually not a big deal here, but write and draw in black or blue ink. I had when I had the first semester, so second semester in civil engineering modeling, I did this for more than 10 years, and I believe there was not a single year where nobody, or not one of them, wrote in red or in green or in pencil. Yeah. So I mean, I said this every time, and they still did it. This is so incredible. We should talk to a, yeah. Okay. So that's the setup. So questions. Questions would be kind of like this. So there would be, for example, 5 points per question is not a must, but I don't like to change my style that much, so I guess it will be of this kind. Okay, so did you have a look at this and you could all solve it? Okay, then how is a conditional statement if then else executed on a SIMD machine? Ideas?
So when I read that question, I was like a little confused because, like, is it about like how would you do it so it uses the whole performance, or is it like because if you put an if else
No.
and any?
If you write if else.
I mean, the code runs in all machines the same, so the if else statement will still be there. It's just when it branches out, different code will run.
The same
Or is there a
instruction.
difference?
The same instruction will be followed by other multiple data.
Instructions. No, but instruction cannot be followed by data. Instruction can only be followed by other instruction.
Yeah, multiple.
Okay, I mean this is something that was explicitly stated in the lecture. What happens if so a SIMD machine can only, so when it does, I mean when it works on vectors, yeah, it can only do the instruction for the entire vector at the same time. So when there is parts of the vector is in the true state and the other part is in the false state. And we only can work on the vector. What does that mean? I mean, it could mean that it's not possible, yeah, but it is possible because somebody said, okay, so this will happen, we will run in this problem, and then they built this into the machine, please.
I remember there's a folio where it said that it's serialized.
Yes, it serialized this.
It just doesn't work like for each, let's say, element of the vector, but for one, that?
No, okay, no. It's okay, so serialization could work in different ways. So for example, then you say, okay, we don't do vector anymore, but we do everything. No, that's not that way. No. It's that both statements are applied to the vector, but parts of the vector can be muted. No? Okay, you should have a look in the lecture notes, yeah? Okay, because we have to go on, otherwise we'll not finish today. So both, I hate this software here. Let me see whether I can write properly. So both statements So today I'm allowed to use my cheat sheet. So both statements execute or are executed sequentially with the threads for which, okay, I could have done this in a little bit more compact sentence, but okay, let's stick with this. With the threads for which my writing is not beautiful in this ugly software here, for which the condition is true, they are muted. So they just don't do the operation. They do nothing. Yeah. In the if branch. And the other way around, of course, also, and the threads for which it is false oh. I did it the other way around, right? Sorry. For which it is, and both statements are executed sequentially with the thread for which the condition is, okay, obviously I made a mistake here. So, the threads for which the condition is false, yeah, they should not be executed in the if clause, right? So they will be muted in the if branch, and the threads for which it is true muted in the else branch. Okay, is this clear to everybody? So it is inefficient, but it's not as inefficient that the entire vector is serialized. Yeah? Okay. Let's go on to have some more time for the interesting things. So a network is organized in an 8-dimensional hypercube. Each node is indexed according to its position. How long is the shortest path between the nodes 0, 1, 1, 0, 1, 1, 1, 1, and 0, 1, 0, 1, 1, 1, 0, 0. So write down the path in the format. Okay, so this is obviously the start node, and this is the end node, and in between the nodes over which we have to transverse to get to this point in the network. Yeah. So there is I suggest to do this part here first, because then when we have done this, we can simply count the steps, right? But if the second part was not here, you could also just see how many steps you need to do by what. I mean, okay, let's start with this. Just look at these two numbers and tell me how many steps. Four steps, yes. And what is the quantity that measures this?
The number of different bits.
Yeah, so this has a name. Hamming distance. Okay, so you just look at the Hamming distance of these two numbers and then you know how many steps. So, okay, let's briefly do this. We have the starting point. So this is the starting point, and now there are obviously multiple ways how you could do this. My just that I don't get confused, I start with the bit on the right. Yeah, so I'll write 0, 1, 1, 0, 1, 1, 1, 0. So that was the first one different. Then we do 0, 1, 1, 0, 1, 1, 0, 0. So this then comes 2 bits which are the same as before, and then comes one that we have to change one. So this would be like this, and then we have 1, 2, 3. So the last one would then be 0.1 or 0, 1, 0, 1, 1, 1, 1, 0, 0. Okay? So, and this is for steps. Okay, so that was easy. What is C? Name 2 measures to avoid race conditions. Which one tends to be more efficient in the sense of being faster? So what do we have? Yeah, mutex and atomic operations. So, yeah, okay. I should, let me see. Okay, maybe I accept, it's better we write this in a little bit more detail. So protecting this being accessed by multiple threads. Sorry for this ugly writing with this toothpick. Through a mutex. So this is of course the important word here. Mutex stands for mutual exclusive. I think it stands for mutual exclusion, actually. Okay, I'm not sure whether it stands for mutual exclusion or mutual exclusive. Yeah. Yeah. So, and 2 is using atomic operations. So which would be faster? So I mean this makes sense because at least for an old guy like me this makes sense, because this is the reason why they introduced atomic operations. So atomic operations have to be implemented in the hardware. Yeah. So when I was your age, there were no atomic operations, but there were of course mutexes. So they thought about how could we do this in a more efficient way. Yes. So I guess. Okay. So that the next one is an interesting question, because I remember that nobody did this write in the exam, even though I thought that is pretty easy. So your network is said to have a latency of 1 microsecond and a bandwidth of 1 gigabyte per second. The total time of transferring 16 buffers of identical lengths between the same two processes takes 30 microseconds. How long will the transfer take if all the data is collected and sent in one event? I mean, this is something that you should usually do. If you have several things that you have to communicate between the same entities, you should group them together, so you should pack them and send them together. Like you would also, if you send something to somebody, to your friend, then you should not send several parcels, but you should put everything in one parcel. So, is this a difficult question? I mean, what's the answer?
Time per buffer is equals to latex plus
Yeah.
bits, number of bits by bandwidth.
I did not get your answer. I mean, there is, okay, so there's of course a number that drops out, right? Yeah, because, I mean, the question is for the number, but we also have to do the calculation. So we send 16 buffers, right? We don't know how big they are. Only we know that they have identical lengths. And all of this together takes 30 microseconds of identical between the same. This takes 30 microseconds. So this is, I think this is what you said, this is the combination of sending the data and the latency. Yeah? So how much latency does this have?
1 microsecond. 1 microsecond.
Yeah, no, this has 1 microsecond latency. I mean, I sent 16 buffers.
16
Then it has 16 microseconds. Yeah? So out of this 30 microseconds, 16 microseconds are latency. So now suppose I sent this only once. How much latency would I get? 1 microsecond. So then what is the time that it takes to send this only once? 50, right. So, okay, you should pass the exam because
What is the gigabyte per second? Because you gave us the gigabyte per second.
yeah, I gave you, no, so
The bandwidth.
the band, okay, so you are confused by having information that is not required. Okay, I mean, so this is something, yes. Okay, we should go on because we'll have to go through the exam. But this is a problem with education, right? So in school, you are trained to this ominous thing that you believe that everything that is given is necessary for finding the result. Think about the real world. In the real world, you don't have a given. You have to collect your information somewhere. Yeah? So, and there's all sorts of information that is not necessary. So whatever you do when you're out of school later, yeah, you never have given and given information for solving your problem. So there is something, actually you can use this, yeah? So you can use this to calculate how large these buffers are. If I ask this too, yeah, so if I made this more difficult by asking how large these buffers are, then you could solve the problem, because then you can use all the information that is in it. Just by asking less, that I ask less, it's confusing apparently. Okay, now good to know for me. So D, so what did we say? We had, we'll have the time for one transfer is 30 microseconds minus 16 microseconds plus 1 microsecond is 15 microseconds. Okay. Apparently it was a difficult question because nobody answered this correctly back then. What is the arithmetic intensity of multiplying an 8 by 8 matrix with an 8 by 1 vector in single precision float? Assume that multiplications and additions are not merged. Yeah, so I have to state this because otherwise the compiler could merge some operations. So we'll count all of them. Okay, so I think this thing is a little bit more tricky, yeah, because you have to know, you have to think about what the matrix vector operation actually does, right? So first, in order to get the arithmetic intensity, we have to get the number of operations. Number of operations. So how many operations do we have if we multiply a matrix by a vector? So what we get out of this are kind of these 8 rows. So we have 8 times 8. Yeah? So we multiply the entire row, so the entire row with the entire column of this vector, right? So it is 8 rows, so we have to do this 8 times. And each time we have to have, so because they have length 8, we have 8 multiplications, right? So is it done after 8 multiplications? Addition. So how many additions do we have? 7. Yes, we have 7. Plus 7 additions. So, what is this? I would suggest 8 times 8 is 64 plus 7 times 8 is 56. So this together will be 120, right? Did I do this right? So then how many bytes are these? It was, let's look in the thing here. So we said float, right? So float has float has 4 bytes. so 4 bytes. 4 bytes. So how many things do we have? We have the matrix. The matrix obviously has 8 times 8 components. Plus we have the vector, which also has 8. So that's 64 and 72. It's 4 times 72. Okay, I don't know whether we want to leave this here because we'll have, okay, I'll leave it with 4 times 72. To the intensity, okay, so what is the intensity? The intensity is the number of operations. So we have 120 floating point operations divided by 4 times 72 bytes. Okay, maybe useful to not multiply this through because then we have to divide anyway. Yeah, so that this goes to, what would this be, 30 by 72 flops per bytes. So we are not using calculator in the exam. So if you leave it at that, that's okay for me. Yeah. So you can. I think this doesn't. You can divide both of this by 6, right? So this this here is 5 and it's the 7. Yeah, 5 by 7. Yeah. Okay. So don't get nervous by these kinds of numbers. Just leave it at 5, 5, 7, or even 30 by 72. It's not. I'm not worried by this. So now I'm running out of space. Here, I've written too large. What is the bandwidth limits of a calculation, and under what circumstances does it dominate the performance of a program? Oh, that's a question where we need to write an explanation, even though we don't have any space left. So if we don't have any space left in the actual exam, what we do is we go to the Zusatzblatt. Yeah? So Zusatzblatt, and this is, now you indicate questions and say that this is the question E, I believe, or is F? Was it F? Yes, questions F. So, questions F. So what is the bandwidth limit? When is anything bandwidth limited? I always have a little bit the impression you are a pretty shy audience. Intensity? When the intensity is low, yes. So this is we can be a little bit more specific than this. So this is when it dominates, when the intensity is low. Actually, when it is so, okay. When you say that something is low, you always have to indicate what would be high. I mean, when is something low, right? This is something like you are, or something is. Something is small, short, light, or something, then you always have to compare this to something. I don't have, okay, so this, you could say that this piece of chalk is short, right? But how do I know it's short? I mean, because we have to, I guess it's short compared to my fingers, yeah? So it's difficult to write with. Yeah, oops. Now I also drop it. You see, this is good for dropping because this does not break when you drop it, yeah? So it's too short for breaking. So, but you know, you jump to the second part of the question. Well, first, what is the bandwidth limit in the first place? I have a little bit trouble with writing here. Bandwidth limits. So bandwidth limits refers to the execution speed, right? So when execution, so when the thing, so okay, obviously we want to have the execution as fast as possible. Yeah, so there is something that limits the speed at which something can be executed. And typically there are two things that may hinder this. The first thing is that the processor cannot do more work. Yeah? So this is what we call compute limited. And bandwidth limited is when the bus cannot deliver more data to the processor. That's the thing that we call compute bandwidth limited. So it means that the execution speed is limited by the speed at which data can be provided to the processor via the bus. So first part. Now when does it dominate? So yeah, if you say when the intensity is small, yeah? So now when we say that intensity is small, we have to compare it to a specific intensity. The knee, right. So it's, and even better to say the knee, because this is could be a part of our body, yeah, is to actually indicate what the knee is. So it dominates when or if, so this is very difficult for Germans, say if the computational intensity is smaller, or say small compared to, then the knee. So we have the knee at the intensity peak performance the peak performance divided by the bandwidth. Yeah, this is the intensity at the knee. So, and when the intensity is lower than that, then we are limited by the bandwidth. Okay, so yeah, this were the questions. Now we have taken much more time for this. But we are talking a lot. Okay, so then comes this thing here, fun question. I always have to think about something strange that has nothing, that apparently has nothing to do with programming. Yeah, sometimes it's collecting T's. This time it's elections. So elections have to be counted. I think I had this exam when we had the last election here. So because I'm in an election committee, so I always have to. Nowadays, since we have digital elections, this has become much easier recently. So in order to accelerate the counting of votes in an election, the ballot papers are equally distributed among P pairs. Okay, now you see that I'm in an election committee because it's illegal that only one person counts votes. Yeah, so they always have to be counted in pairs. P pairs of people counting the votes in parallel. Afterwards, one pair of people sums all the counted votes together. Counting a vote takes 10 seconds, while adding the votes to one pair, the votes of one pair to the total takes 40 seconds. Maybe that's not realistic, but just get some numbers. Yeah, the expected number of votes is n equal to 100. That's also not very realistic. Okay, but anyway, these are just numbers to fill in the equations. So, what is the speed up of the proposed procedure as a function of p compared to counting all votes sequentially? Now, you have potentially you have different ways of thinking about this, yeah, which gives you different answers. Yeah, so one possibility is to think about this, whether this is strong scaling or weak scaling, right? And then pick the right equation for this. Now, unfortunately, with the reality is that many of these things are not either directly strong scaling or weak scaling, right? And then still you have to look in this. So is this strong scaling or weak scaling? The problem here is that it's actually neither, because when you parallelize one part, then the sequential part becomes, then if you parallelize more, the sequential part also becomes larger, because afterwards you have to count these votes, these partial sums again. Yeah, so I mean, this is completely realistic. Yeah, so this can happen. Something like this obviously can happen in your program too. Yeah, that you can neither say that this is strong or weak scaling. So because it's neither strong or weak scaling, what we should do is to write down the numbers directly and say, so what happens in TP? So T in parallel, what will it take? So we have to count the votes. All the votes counting takes 10 seconds times the number of votes that we have divided. So each pair, so P, the number of pairs, so this is what the parallel part, yeah, so they get N divided by P votes that they have to count, right? But then there is the sequential part, and this is why this is neither strong or weak scaling, yeah, because this now goes P times 40 seconds. Okay, so the reason why there are lots of, why this takes so long is, of course, because there are many candidates that you have to put in the list. Otherwise, I mean, yeah, it wouldn't make sense that it takes so long. So, sequentially, what would happen sequentially instead? Sequentially is just, so this is supposed to be an n times 10 seconds, yeah? So this is when everybody takes takes their, so it's just one pair calculating all of this. So then our speed up, by definition, this S is the sequential time divided by the parallel time. And now you put these things here, so get n by p times 10 seconds plus p times 40 seconds divided by n times 10 seconds. I have the tendency to write this in a format that I kind of prefer here, dividing by p, so that it becomes n times p times 10 seconds. So you see, apparently this is an NP hard problem. Please, did I have made a mistake?
It should be sequential divided by the parallel. Now it's parallel divided by sequential.
It's sequential divided, yes. Thank you. Okay, do everything again. Right, so it's, sequential n times 10 seconds divided by, okay, let's just write it already like this. 10 seconds times n plus 40 seconds, right? So still a mistake?
It should be plus 40 seconds times p squared.
Times, because I p squared. Thank you. Okay, sorry, yes. So by p squared. So if we now, you see, so if we even take the limit of this, actually we did not ask for the limit, but okay, let's limit when p goes to infinity, just to get a feeling. Yes, this is what I said, it does not. So, I have hardware problems today, as always. So this would, for getting fast, I'll just, you see that this gets to 0, yeah? So in the infinity, if we try to over-parallelize it, so we don't get any speed up anymore, right? So we can kill it with too much parallelization. Okay, but we got the speed up, so this was the answer for question 1. And now question 2 is at what value p does it take the least amount of time to know the result? So how do we do this? Derivative, yeah. So we take d by d, we take t by d onto tp. So then this was here 10 seconds n divided by p plus p times 40 seconds. Okay, so I did not write it. Okay. Of course. This gives you the p down here will disappear, and the p in front here, 10 seconds, will become minus p squared, right? Plus the 40 seconds. So. And I mean, this is why you said will take this. So what's to do? We put this on the other side, take the inverse, so that would be like n divided by 40. No, it's not n, it's 10 times 10 seconds times n divided by 40 is p square, right? Okay, and then if we want to have p, then this would be n, so 10 seconds by 4. So, okay, that would be the result. And now we got a number for n. The number for n was 100. That's 104, and I guess, so this kind of problem you have to be able to solve without a pop calculator. I guess this is 10 divided by 2, and this is 5. Yeah. So if you have to count 100 volts like this, then you should split up your, and then you should have 5 groups. That would make it the quickest. Yeah, and then you see if you go further, then your speed up goes actually down to 0 in the limit. Good. So you have to live with some crazy question like this. And now we come to the actual. Now we are all okay. So this is typically what happens in the exam. Now you're already more than half through with your time, and you have not started with the interesting questions. Okay, CUDA. So since we have only 4 of these questions, I can usually not cover all of the things that we had. Yeah, but remember we have MPI, so we'll definitely do MPI because this was too central. Yeah, but then we have CUDA, we have threads, we also have some atomics, and we have OpenMP, and some of them will probably not come, and others will come. And so anyway, in the following snippet of CUDA code, the simulation procedure was previously computed on the host and is now moved to the GPU. Write the necessary CUDA function simulation routine that has the same functionality as the commented part. So, okay, so this is how this was done before, and now it is done in this line here. Now we have to replace these things here, and now there is this loop. Okay, what does it do? We have two arrays of integer. Yeah, so they are allocated here with the size 1024. Yeah, so hopefully, this is what we hope, that 16 times 64 is hopefully 124. Yeah, so otherwise that would be strange. Yeah, so and then we have the loop, which kind of looks like a little bit of finite difference scheme. Yeah, so you take one index and subtract the previous index of this and put it into the, oh, there's definitely a mistake here. Oh my God. There's definitely a mistake. Yes. Okay. So first of all, ask the professor, is this supposed to be like this? Okay. I mean, this would try to override the address, right? Yeah, so because this is a pointer. Okay, so this, if you see something like this should be a mistake. Where have we been? Right, so, and now we should do this with this code here. Actually, And then there is one exception. So this exception is a problem. Yeah? What I did not ask you to write a very efficient code here. So we'll somehow deal with this exception now inside our CUDA code, even though this may not be the most efficient way. So I didn't ask for efficient thing. So what we have to do is we have to define a global function, obviously. Yeah. So there must be two underscores, global, two underscores, and this thing has already a name. Fancy in Italy, wait. No, it's this one, yes. So, simulation routine. Don't be stupid. It has to be of kind void. It has to be of kind void, and then comes simulation routine. So, what does it get? Data in is a double. Yeah, is a double. Pointer to a double. And then it gets the same thing, double dot, is it called that way? Yeah, dot out. So by using the same names here, I can just use, I mean, I could have given their other names, yeah, but I'll stick to these names. Now, okay, so first things first, we get this in this, you see, this is the thing that I have to think about myself all the time first. So this is the number of blocks and this is the number of threads, right? Yeah, and it's one-dimensional, yeah? So we could have this three-dimensional, but we did it one-dimensional. So then with calculating our index, we could also just do this in the same way and just use the one-dimensional version of it, not doing more, because we need to know our index. We need to know where we are. So this is what we start off, and this is something that you should look up and have in your mind. Yeah. So how to calculate such an index. So what we do, because now we are only one-dimensional, we use only one of them. And yes, we know. Yes, we use block ID. It's not the block ID, it's the block index. This is why this is block EDX. Yeah? Not, you see, there's two X here. Yeah? The one is from the name because this is block index, and because we have only one dimension, we'll take only the X one, but still we have to write X here. X, so, and this we always have to multiply with the block dimension, and also this in X. So this block dim dot X. And then we add to this the thread IDX. So this is how we usually do this. You see that you could potentially do this also in a different format when this gets. It would be easier for whatever reason, but this is what we usually do to identify our index. So now we have the trouble that there is an exception. Our loop starts from 1 that we have here. So this loop, where's our loop? The loop actually starts from 1, so it's only taking 1023 cases, and one case is an exception. Now we can do something inefficient that is related to the first question that we had. Yeah, because we are in a SIMD world, and still we are allowed to use a conditional statement. When we do it this way, so actually what would be more efficient is to do the first index on the host, yeah, and just let the other parts be done on the device. But now we did it this way. So we ask if I is equal to 0. Then do this, that out. So, okay, here we made this mistake. Don't make the mistake again. So this is not, no. I mean, this would be possible, but yeah, well, it would be the same, actually. So that's, what is this? Date. We have to look this up. Date. So date out 0. No, it's not date out, it's date in. Date minus date in 1000. Okay, so this is pretty bad style, yeah, to have hard-coded numbers here, but okay, we'll do it this way. So now this is pretty bad, because now all the other threads, at least all the other threads in the same warp, will have to wait for this to happen. Yeah. So anyway, we did this. Else we do the other part. So else is that out I. So let me see, what was the program. That out I is that in I minus that in I minus 1. Well, yeah, and that's it. And I guess that's it. As it is not a 3, this is supposed to be in curly brackets. Okay? So this is how you could, for example, solve this problem. Good. I'm charging my pen. While we go to our next question, unless you have any questions. Asynchronous communication. The following program delivers indeterministic results. Okay, let's just go briefly describe the mistake that leads to the indeterministic behavior. Describe what to change to avoid the problem. Okay, so we have, what does it mean, indeterministic?
The result might change under the same circumstances?
Yeah, so you run the program several times and you get several different results. Yeah, so this is indeterministic. Okay, so we initialize, we get rank and size. Yes, we got them. We put the rank into the data for whatever reason. Then we have a request, status, and then if we are rank 0, then we do an asynchronous send, yeah, with immediate return. Yeah? And because it's asynchronous, we have a request here. So then If it's not that, we send something else, and then we wait for this request, and then we do the same thing again and again. So and then we wait again. Or we wait several times. So do you already see what the problem is? I mean, I entered this. I used so part of the reason why I have this question here is because this was such a common mistake the previous year in the homework. Yeah, so when you've already done your homework, you may have done the same mistake, which means that I did not explain it very well. We have some trouble with this, and this is something that I have seen a lot of times in the homework. What is the request good for? You, please.
Oh, what was the question?
What is the request good for?
For identifying the request.
To identifying what?
Who, I mean, in this case, it's for identifying which request we are waiting afterwards.
Yes. Okay. So it's right. That's right. So it's for identifying what we are waiting for. Yeah? So then we come to wait. We come to wait. And what is this wait waiting for?
So it's going to wait for this request, but there is a problem here because ranks in between 0 and the last one are going to send 2 requests. And this request is waiting for a request, but it could be any of those, so it's probably going to be the first one that arrives.
No. I mean, they don't send a request. You think they send a request. They are not sending a request. Request is not sent. Receive. Okay, so you mean in the receive we also have a request, right? Yes. It's always the same request. Yeah, it's like you go to a government office and you get these numbers, you know this, and they always give the same number. No, that's not. Okay, that's not a compatible. This would behave in a different way. Yeah. So I mean, this is what people. What I think this is what the person who wrote this was intending. Yeah, that we wait for all of them. Yeah, but this is not what happens. Because if we set a request here, then we override the previous request. So we'll always, so because I said it will wait for the first one. No, it will wait for the last one. Yeah? Because we override this. So there's one this is like there's one piece of paper for everybody and it's just overwritten somehow. And so then suppose this here is done and this is not done. Yeah, then this behaves in a different way because we are not waiting for this. Yeah, we are waiting only for the last one. By the way, this may work very, very often. Because this may work very often because this here may already be processed because it was sent off before, yeah. So this may be quicker than that one, and then it may just work, but there's no guaranteed that it works. So, and then you have, this is the trouble with these things, that they seem to be correct because they work 20,000 times out of 20,001 time, yeah? And then they are still incorrect. And if this is how can it be that for example, operating system like Windows crashes? It has been tested. I mean, it's used by so many people. Yeah, it has errors like this. Okay, so the problem being the wait statements. The wait statement only waits for the last MPI call. That overrides the requests. From the previous call. So what can we do about this? Of course, we can use individual calls, yeah? So this is, what can I do about my pen not working? No, not individual calls, individual requests. So use individual requests. So you can also put them in an array, yeah, so you can put your requests in an array that may be useful if you don't have a control over how many there are, or you can put them in a vector, but this is not required in this case, I think. So then, for example, you could call wait all to be more accurate, you could call MPI wait all. With all the requests. Okay, so look at your homework, whether you have done this properly, and then still have time till Sunday. Okay, so this was here. Now it becomes more involved. It's also a bit more points here. All gather. In the following code, comment out the MPI all gather command and replace it using only MPI send and MPI receive functions. So this is admittedly a more involved question. Yeah? So I highly recommend, if you ask, so what can I learn for the exam? Yeah? So I don't have that many options that I make as exam questions, and anyway, this is a good training. Think about all the different functions that you have in send functions that you have in MPI, like you have broadcast, gather, and what was it, the reduce, right? Yeah, all these things. You have all gather, you have gather. Yeah, think about it. Suppose they are not there. How could I do the same thing they do by other means? Yeah, and then from this, think about different possibilities, and then as an exercise for you preparing for the exam, try to write this down by hand. Yeah, you can also check it on computer later whether this is correct, but try to write it down by hand, because this is what you need to do now in the exam. So what is happening here? We have in main, we initialize, we have size, MPI com sim command. So so we get the rank. Okay, each process will have an array of size 3. So we get, okay, actually it's written array, but there's a vector, int, send data, and then we put some data in it, so whatever. Then we have the receive data. So the receive data, because it is sent to everybody, it's 3 times the size. So size is the number of rungs that we have in the system, right? So perform the all gather operation. So this is now the thing that you're supposed to replace. Okay, by the way, there is a joke here, but this is true. There is comment out, yeah? So what you have to do is you have to comment this out. So you have to do this. Wait, if I could do it. You have to do this, and you get 1 point, okay? So, comment this out. If you forget it, no point here, yeah? There are now different, I really recommend that you think about these things before the exam and have something in mind already, yeah? How you can do this, because there are different ways of doing this, of replacing these things. Yeah, because now we have to communicate from everybody to everybody, yeah? And this, if we communicate from everybody to everybody, which we can do, and which potentially would be the more efficient way, potentially, I'm not sure, then we also have to take care that we don't get into a deadlock. Yeah? So I did not ask you to do it the most efficient way, just do it somehow. Yeah? But do it in a way that is correct without a deadlock. So one way that can be done is to decide on a master process that first collects all the data and then sends it out again to the others. Yeah, I put this yesterday. I also put this to ChatGPT to see what solution they would come up with, and it was a different solution. So now I noticed there are different ways of doing this. Yeah, but let's do it my simplified version here. Yeah. So if we decide on a master process, and obviously we always take the rank 0 because this always exists. We take the rank 0 as the master. So we look at if we are 0. Then we want to collect everything. So if we collect everything, so we have to collect from all our neighbors, so we have to go through the loop. So for int, now important because we are rank 0, we have to start from 1, right? So we have to start from 1. And we have to stick smaller than size, because size is the size of the of our world here, yeah? and then we have I plus plus. So there was, so when I first, or when I yesterday tried this out again, first I was thinking that I should increase I by 3, because I would iterate over the vector, but then I noticed this is stupid. No, don't do this. We rather iterate over the ranks. Yeah. So we iterate over the ranks, and then we have MPI receive, because this is what we are allowed to use. MPI receive. So in here, I'm not able to write this letter properly. So this is this end. Yeah. So the, what is it called? The reference operator. So here we have to get this into our receive data, yeah, into this thing here. So receive data. Okay, so how is this done here? So we can put data. This gives us a pointer. This gives us a pointer to the by the way, now I'm not completely sure whether I need a bracket here. I think I need a bracket here. Better use a bracket. Receive. So this gives us a pointer to the first entrance. Yeah. Now. So how do we do this? We have this entire matrix, this entire vector, and we want to plug in parts of this from the different ranks, right? So we need to point at the point in this vector at which we want to load it. So, and this is the start of the array. If this is the start of the array, then we have to go on. So we have to count this up. Yeah. So we know that each rank sends 3 pieces of data. Yeah. So what we have to do is we have to add here 3 times I. Yeah, so this will start because I starts with 1. So this will start at position 3. Yeah, because this here is at position 0. So, okay, I think we need the bracket because this is added onto the start of the array here. Yeah. So how many data do we send? We send 3 data. We send data of type MPI int. MPI int. Okay, this has to be written in capitals. MPI int. So what's next? Next is where we get the data from. That would be I. Do I make this cheat sheet? Yes. So what is after the index? Peg. Okay, so we don't use tag, just put it to 0. More elegant would be to define it somewhere and say, yes, this is our tag. So, and then we need to have the communicator, this MPI com world, and then because it's a receive function, it also has a status, and because I don't want to deal with the status, I just say status ignore. So I guess that's it. NPI status, and yes, you are so right. NPI, they all start with NPI. No, okay, now everybody sees that I made this mistake and had to correct. So we are through with this. We are through with the loop, yes. So actually we have to do something annoying here. Namely, we have to load our own data of the zero process into our. Actually, I'm not sure. Maybe it does this when we start with zero. I don't know. Does it send to itself? I don't know. I would have to try. I don't believe in this and just wait. The reason, okay, so this is, I now do this. Okay, I'm so old. I learned actually programming in assembler. Yeah, and so we have to do. So if we had to do things 3 times, we just write things 3 times. Yeah, that's. We just copy the first 3. So don't bother. Just do. There must be a more efficient way to do this. So now we have also copied the first 3 of them. So after we did this, we also have to send we also have to send it back to all the others. Actually, this again here doesn't fit all in this place here. So we have to send it again. This is we can only send it after we collected everything. So we need a second loop, right? So we'll do again the same thing for int I equals to 1, I smaller than size, I plus plus. And here we do MPI send. So we use our send data dot data. Now we send all of this to everybody. So it's 3 times the size, and it is MPI int, and we send it to I, we send it with the tag 0, and we use MPI world bracket close, and now we also close this bracket here. Okay, looks a little bit ugly, yeah. So this bracket here is the one closing for this. Now we've received everything. So process 0 has received everything and sent it out again. And we are running out of space here. So what we do is say Zusatzblatt 2. Now you're also supposed to learn some German here. Now Zusatzblatt is a very important German word try to find it in the dictionary. Zusatzblatt 2. So, we were in the if clause, now we are in the else clause. So else means we are not run 0. Yeah, so now we first have to send stuff to the waiting process 0, MPI send. So what do we send? We send, oh wait. Okay. I forgot the address operator. And I,
I think the address operator is not needed because .data returns a vector. Oh, returns a array pointer.
yeah, it returns a pointer, right? And then
it's already
oh, yes, you're right. Okay, sorry. Okay, so the way you should notice this. Okay, yeah, thank you for correcting me. Yes. Let me see, what does my cheat sheet say? Okay, apparently I was confused because sometimes I write it and sometimes I don't write it. Okay, maybe I should, in order to avoid this, I should potentially just print out something that ChatGPT produces. The stupid thing with this is that this actually during the last year or so has improved to the state that I would assume that it is mostly correct for some simple things like this here. Yeah, but I mean I'm trying this out a lot and often it is not correct. Yeah. The problem is also just for the homework purposes. Okay, I'm wasting the time, but anyway, this is the things that we give out as homework. They are so simple and they have been done so repeatedly, so often that they are so often outside in the world that what we give out as homework can always be done by ChatGPT or all these things. So this is a didactical problem because now you could say that everything that we teach can be done with a machine, but we teach this in order to get you do simple things. So this is like using a pocket calculator. Everything that you learn in primary school in doing calculations can be done with a pocket calculator. Yeah, so why bother? Yeah, but if you don't understand these things, because if it's getting more complicated, then ChatGPT also stops working, at least so far. So, I'm confusing myself. We are in the else clause, right. So, we are in the else clause and we have to, and the problem was that because this is already the pointer, we don't need to write this, so we have to send data.data, and we send 3, and they are of kind MPI int, and we send them to rank 0, we send them to with tag 0. Now, since we previously decided to use tag 0, it's now important to use tag 0 again, otherwise they don't match up and they will not communicate. Then MPI com world. Okay, so once this is done, Once this is done, we can immediately go on to receiving from the rung 0 by MPI receive. So we put this into our we do this into okay, my cheat sheet has a problem. We put this into our receive data dot data. We are expecting 3 times the size, and they should be of kind MPI int. We are expecting this coming from 0. We are expecting this coming from tag. With tag 0, we are using the MPI convert communicator. And then there's one last thing that we have to add. And then we have to do something with the status. And since we did not, okay, MPI, sorry. Since we did not define a status variable, what we do is we do MPI status ignore. Check. So. And that solves this problem. Yeah? And now, this can be, this can be very similar in the actual exam, that we usually don't talk that much in between, but still you could see that the time, that the 90 minutes are actually over. So what you cannot see, and this is, I'm very sure, that 100 minutes are already over. I'll take your paper away after 90 minutes. So anyway, time would usually, so could be that you cannot do everything in this time. You should always, of course, try to do everything so as you should go as far as possible, of course. Now we come to the last. So we of course we still do this here. Threads. Yeah. It's a little bit stupid example, but anyway. Write the following program using include threads and include mutex, with the first and second loop being executed by thread A and thread B respectively, introduce and use mutexes where necessary. So rewrite the code means that we have to, that we don't need to, we are not changing it, but we have to write it again. So there's a lot of writing involved in this. Yeah. So this is why I put this to the last thing. So if somebody is very quick, don't fall asleep during my exam. I've seen this. People sleeping in my exam, actually waking up later and continue writing. This really happens. I mean, do be a professor for what is, doing this for 16 years now. Yeah, I've seen this a lot. I've seen everything. So, okay, we have to write. So first things that we have to write. You may get partial points here. Yeah, is we have to include. I mean, this is what was written. We have to include. Thread. And we have to include mutex. So, and now we have to write functions that do these loops. So what do the loops do? There is a vector, an array A, an array B, and an array C. And I mean, of course, this makes absolutely no sense to put this into different threads. Yeah, it's just for example that you know. I mean, this is horrible inefficient. Yeah. So first loop, what does it do? It adds A to C, and the second loop is adding B times 2 to C. Now there we have to define these functions here. So for these things we have to define functions. Okay, I leave a little bit of space here for something that I want to introduce later. Yeah, and we have to define these functions. So they need to be of kind voids, and because we are late in the exam, I don't know, I just call them func, or you could call them f if you wish. Yeah. So now, running late in time, I could think about being more efficient in my writing and say, okay, these two loops, I mean, can do this in different ways. You can write func A and func B, yeah? And because they are so similar, what I'm now going to do is I write only one function with a parameter here. Yeah, so this is not necessarily the best solution, but it's the one that I'm going to take here. Yeah, so I have an integer. These are integers. Yes, they are integers. Integers. So I take the matrix M, and I take the matrix array C, and I take an int factor. Okay, then I write this thing inside here. So for int I equal to 0, I smaller than 5 plus I. So again, I leave a little bit of space here and write ci plus equal to factor times m. So then I can implement both of these guys here together. So now both of these guys will try to write onto the same matrix C. So then, in order to avoid the erase conditions, we are supposed to introduce a mutex, and that the mutex is accessible. I now have different options. I could hand my mutex as an attribute of this function, which I've now not done already because I wrote it here. So I could also do it statically. This is again not the best style potentially, but for such a short program, what I do is I have a static mutex. Let's call this, okay, I call it mx. Yeah, so this is outside any function in the beginning of my file. Yeah, before I call this function. So I have it now here. What I can do is I can lock this before I do anything. And I can unlock it after I was doing anything. Okay, I have to admit that this is so ridiculously short that in practice you would never do it like this. Yeah, but for the purpose of illustration, yeah, because otherwise we cannot do this in the exam. So now this will take care that when this is called from different places, that they will not that they will not try to write at the same time. So having implemented this, we come to our main. In main, so here again we have to, okay, I'm being annoying because now what you have to do is you have to write all of this that was written before. In B 6, 7, 8, 9, 10. And in C, I guess is 0, 0, 0. This is fine. One more. So there are supposed to be 2 threads. So standard threads, let's call the first one T1. It takes the func. So, and then it takes the A matrix, it takes the C matrix, and it takes the factor of 1. Right? Right. And then there's another one, standard threads T2. Func is taking the B matrix, the C matrix, and it takes the factor 2, I believe. So it's this here, factor 2. Yeah. Okay, so we don't forget the semicolon. Never forget the semicolon. So now we have to join these guys again. Good style is to check whether they are joinable. This is not completely, I mean, it will also work without this most of the times. So if it's joinable, then join it. If T2 is joinable, then T2 dot join. So running out of space, but we don't need much more. The only thing is, because it's int main, we have to return an integer. To return 0, and then we close the bracket, and then we are done with our exam. So, any questions that should be on the recording? Any question? Otherwise, the recording will now stop.